The morning of May 8, 1942 dawned clear over the Coral Sea. Aboard the aircraft carrier USS Lexington, Machinist Oscar W, Myers finished his pre-flight inspection of the fuel delivery lines running from the keel tanks to the hangar deck. Everything checked normal. Pressure gauges read steady. No leaks in the brass fittings. The topside gasoline lines, stretching hundreds of feet through the ship's ventilation trunks and up to the flight deck fueling stations, were ready to pump 100-octane aviation gasoline into the carrier's aircraft for the morning strike. Myers was the ship's air fuel officer, responsible for every drop of volatile gasoline that flowed through Lexington's circulatory system of pipes and pumps. It was a job that kept him awake at night. He understood something most naval architects designing these ships back in Washington didn't seem to grasp. Aviation gasoline wasn't just flammable. It was an explosive waiting for the slightest excuse to detonate, and the Lexington was carrying 330,000 gallons of it, stored in tanks surrounded by seawater ballast, distributed through miles of piping that ran through virtually every deck of the ship. At 11:13 that morning, Japanese torpedo bombers appeared on the horizon. By 11:20, 2 torpedoes had slammed into Lexington's port side. One struck between frames 60 and 65, directly into the port gasoline storage tanks. Myers felt the explosion reverberate through the steel deck beneath his feet and knew immediately what had happened. The aviation fuel tanks had been ruptured. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Myers couldn't see, what nobody aboard Lexington could see, was the gasoline now mixing with seawater in the ruptured tanks below. The torpedo had cracked the fuel containment, and gasoline was seeping into damaged compartments, finding its way into ventilation ducts, rising through the ship's internal spaces as invisible, deadly vapor. The ship's damage control parties sprang into action, sealing hatches, fighting fires, transferring fuel from port to starboard tanks to correct a 7-degree list. Within 80 minutes, they had the carrier back on an even keel. Flight operations resumed. Aircraft returning from the morning strike landed safely. To the officers on the bridge, it seemed they'd survived the worst of it. Myers knew better. He'd been monitoring the fuel systems since the torpedo strike, and the indicators weren't making sense. Pressure readings in certain lines were fluctuating. The ship's gasoline control room, located on the second deck just aft of the forward elevator, had been secured and flooded with carbon dioxide as a precautionary measure after inspectors noted potential damage. But the miles of piping that distributed aviation fuel throughout the ship, those trunk lines running up through 5 decks to reach the flight deck refueling stations, those lines hadn't been properly drained after the last refueling operation. Standard operating procedure called for those lines to be emptied after aircraft fueling was complete. But in the chaos of preparing for combat operations, with planes launching and recovering constantly, those lines often remained pressurized and full of gasoline. Or worse, partially empty, creating exactly the conditions Myers feared most. Not liquid fuel, which was relatively safe, but vapor, the explosive mixture of gasoline fumes and air that could turn a steel warship into a bomb. At 12:47, nearly 90 minutes after the torpedo strikes, Machinist Myers was still monitoring the fuel systems when the first massive explosion erupted deep inside Lexington. The blast originated in the I.C. motor generator room on the second deck, a space packed with electrical equipment generating sparks as motors ran pumps and generators. Gasoline vapor that had been slowly accumulating in that compartment, leaking through damaged hull plating or rising through ventilation ducts from the ruptured tanks below, had finally found an ignition source. The explosion killed 25 men instantly and knocked out the ship's main damage control station. Fire raced through ventilation trunks, following the paths of gasoline vapor that had been spreading through the ship's internal spaces for the past hour and a half. At 2:42, a second massive explosion ripped through the forward part of the ship, this one even more violent than the first. More fuel vapor had accumulated. More spaces had become saturated with explosive gas, and now those spaces were detonating in sequence. A third explosion followed at 3:25. Captain Frederick Sherman, commanding officer of the Lexington, stood on the bridge, watching his ship die from the inside. The fires were beyond control now. Torpedo warheads stored in the after hangar were beginning to cook off from the heat. The carrier's enormous aviation fuel reserves, the very substance that gave her aircraft their reach and striking power, had become the instrument of her destruction. Not from enemy action directly, but from the secondary effects of that action, from the gasoline vapor that nobody had thought to eliminate from the ship's fuel delivery systems after the initial torpedo damage. At 5:07 that evening, Sherman gave the order to abandon ship. 2,735 officers and men evacuated the Lexington, transferring to destroyers and cruisers standing by to rescue survivors. Sherman himself, observing the traditions of the sea, was the last man off, departing at 6:30. The destroyer USS Phelps put 5 torpedoes into the burning hulk to scuttle her, preventing capture by Japanese forces. At 7:52, the Lexington rolled over and sank, taking with her 216 men who'd gone down during the explosions, along with 36 aircraft. The official loss report, compiled by the Bureau of Ships in June 1942, documented everything. The torpedo hits, the subsequent flooding, the damage control measures that had seemed to work, and then, buried in the technical analysis, the conclusion that would haunt naval architects for the rest of the war. The catastrophic explosions that destroyed the Lexington had not been caused by the initial torpedo damage. They'd been caused by gasoline vapor accumulating in spaces throughout the ship, vapor that had leaked from ruptured tanks, and more significantly, from the ship's own fuel distribution system. The trunk lines that carried aviation gasoline from the keel tanks up to the flight deck, lines that ran through the ship's ventilation system, had not been properly secured after the torpedo strike. Those lines had continued to vent gasoline vapor into internal spaces until the inevitable spark found the inevitable fuel-air mixture. The report's language was bureaucratically careful, but the message was unmistakable. Every aircraft carrier in the US Navy was vulnerable to the same failure mode. The ships were designed with elaborate fire suppression systems, damage control stations, watertight compartments, all intended to keep them fighting after taking hits. But those systems didn't address the fundamental problem that had killed the Lexington. Gasoline vapor in the fuel delivery system itself, invisible and undetected, could transform any carrier into a floating bomb waiting to explode. When the survivors from Lexington reached Pearl Harbor in early June 1942, Myers was among them. He'd spent the voyage back thinking about those fuel lines, about the vapor accumulating in spaces that nobody was monitoring, about the 25 men killed in that first explosion when spark met fume in the generator room. He'd been thinking about it since before the Lexington went down, actually, since the moment the torpedoes hit, and he'd realized that the ship's fuel systems had no way to eliminate the explosive vapor from the distribution lines. Myers understood the chemistry. Liquid gasoline isn't particularly dangerous. It doesn't burn easily, doesn't explode. But gasoline vapor, the fumes that evaporate from liquid fuel, those are deadly. Gasoline vapor mixed with air in the right proportions, between 1.4% and 7.6% fuel vapor by volume, creates an explosive mixture that will detonate with devastating force given any ignition source. An electrical spark, a hot surface, even static electricity in the right conditions. Aircraft carriers were floating gasoline depots. The Essex-class carriers under construction would each carry over 300,000 gallons of aviation fuel. That fuel had to be stored safely in tanks, then distributed throughout the ship to reach the flight deck fueling stations where aircraft would take it aboard. The distribution system consisted of pumps in the lower decks, forcing fuel up through vertical trunk lines, sometimes 5 or 6 decks high, to reach the flight deck. When those pumps shut off after refueling operations were complete, gravity would drain some of the fuel back down into the storage tanks. But the lines themselves, hundreds of feet of piping running through the ship's interior spaces, would retain residual fuel. and that residual fuel would evaporate, turning into vapor that filled the pipes and, if the system wasn't perfectly sealed, leaked into surrounding compartments. The Lexington's destruction had proven this failure mode catastrophically. Myers had watched it happen. He'd seen the pressure readings fluctuate, indicating vapor formation in the lines. He'd known the danger was building but had no way to eliminate it under combat conditions. Now, back in Pearl Harbor, he had a chance to do something about it. The USS Yorktown, sister ship to the Lexington, was in port undergoing repairs from damage sustained at the Battle of the Coral Sea. Yorktown had taken a bomb hit that punched through her flight deck, but she'd survived largely because she hadn't suffered the same fuel system catastrophe that destroyed Lexington. Myers went to Yorktown's engineering officer with a proposal so simple it seemed obvious in hindsight. Replace the air in the fuel distribution lines with carbon dioxide. Purge the gasoline vapor out of the system using an inert gas that wouldn't support combustion. Make it physically impossible for an explosive mixture to form in those fuel lines, regardless of how much residual gasoline remained in the piping. The engineering officer's response was immediate and predictable. No. The Navy's fuel system specifications didn't include any provisions for CO2 purging. The lines were designed to be drained by gravity after use, with residual vapor venting through the ship's ventilation system. Adding separate, inert gas distribution network would require modification to the ship's existing systems, running new piping, installing CO2 storage tanks, adding valves and controls. Yorktown was scheduled to return to combat operations in a matter of days. There was no time for experimental modifications to critical systems. More fundamentally, the engineering officer explained, the Bureau of Ships would need to approve any modifications to fuel handling systems. This wasn't something a single machinist could decide to implement on his own authority, regardless of how sensible the idea might seem. There were regulations, specifications, approval processes. Myers understood what he was hearing. The system that had killed the Lexington would remain in place, unchanged, on every other carrier in the fleet, because making a change required bureaucratic approval that would take months to obtain. But Myers also understood something else. The Navy had just lost one of its 3 operational aircraft carriers in the Pacific. Another carrier, the Saratoga, was in port being repaired after a torpedo hit from a Japanese submarine. That left exactly 2 fleet carriers available to face the entire Imperial Japanese Navy, the Enterprise and the Yorktown. Intelligence reports suggested the Japanese were planning another major operation, possibly targeting Midway Island. Yorktown would be needed for that battle, and if Yorktown went into combat with the same vulnerable fuel systems that had doomed the Lexington, there was a very real possibility that sparks from battle damage would find gasoline vapor in those distribution lines, and the same sequence of internal explosions would gut another American carrier. Myers made his decision that afternoon. He was the air fuel officer. The gasoline systems were his responsibility. And if the engineering officer and the Bureau of Ships weren't going to authorize a modification that could save the ship, then he'd implement it without authorization. Yorktown had carbon dioxide fire suppression systems already installed for fighting fires in machinery spaces and fuel storage areas. Large CO2 bottles were stored throughout the ship, ready to flood compartments with inert gas to smother fires. Myers began quietly rerouting some of that CO2 capacity. Over the next 72 hours, working with a small team of machinists and pipe fitters who understood what he was attempting, Myers fabricated a makeshift CO2 purging system for Yorktown's fuel lines. They ran small-diameter copper tubing from the existing CO2 storage bottles to connection points on the main fuel distribution trunks. Simple valves controlled by the fuel handling crew would allow CO2 to be injected into the fuel lines after aircraft refueling operations were complete. The inert gas would flow through the system, displacing both liquid fuel and gasoline vapor, pushing it back down into the storage tanks where it belonged. The lines would be left full of carbon dioxide, an atmosphere that contained zero oxygen and therefore could not support combustion under any circumstances. The system wasn't sophisticated. It didn't require exotic materials or complex engineering. Myers used existing CO2 supplies, standard brass fittings, and copper tubing that was already stocked in the ship's machine shop for other repairs. The entire modification probably took less than 40 hours of actual work time, spread across 3 days of Yorktown's availability in port. When it was complete, it was barely visible to anyone not specifically looking for it. A few extra pipes, some additional valves, connection points that looked like they'd always been part of the original fuel system design. Myers didn't ask for permission to test it. He simply began using it. After each refueling evolution, once the aircraft had taken on their fuel and taxied clear of the fueling stations, Myers's crew would open the CO2 valves and purge the distribution lines. The procedure took perhaps 90 seconds once the valves were opened. Carbon dioxide flowed into the fuel trunks, displacing the residual gasoline and vapor, forcing it back into the storage tanks. Pressure gauges confirmed that the lines were fully purged. The system worked exactly as Myers had designed it. The Yorktown's commanding officer, Captain Elliot Buckmaster, learned about the unauthorized modification 2 days before the ship was scheduled to depart Pearl Harbor. Myers was summoned to the captain's cabin to explain why he'd modified the ship's fuel systems without engineering approval or authorization from the Bureau of Ships. Myers laid out his reasoning. The Lexington had been destroyed by gasoline vapor explosions. Those explosions had originated in the fuel distribution system. Every carrier in the fleet was vulnerable to the same failure mode. The CO2 purging system eliminated that vulnerability by making it physically impossible for explosive vapors to accumulate in the fuel lines. It used existing equipment, required no exotic materials, added negligible weight to the ship, and could be operated by the existing fuel handling crew with minimal training. Buckmaster listened to the entire explanation in silence. Then he asked Myers one question. "Does it work?" Myers answered yes. The captain's response was equally brief. "Keep it." On June 1, 1942, the Yorktown sortied from Pearl Harbor as part of Task Force 17, heading northwest to defend Midway Island from the anticipated Japanese attack. Myers's unauthorized CO2 purging system went to war installed in the ship's fuel distribution network, unknown to the Bureau of Ships, unapproved by any naval architect, and unmentioned in any official documentation. 3 days later, at the Battle of Midway, that system would be tested under the most extreme conditions imaginable. The morning of June 4, 1944, Yorktown's crew was at battle stations before dawn. Intelligence had confirmed that a massive Japanese carrier strike force, 4 fleet carriers with over 250 aircraft, was approaching Midway Island from the northwest. The U.S. Navy had exactly 3 carriers to oppose them: Enterprise, Hornet, and Yorktown. The Japanese had no idea the Americans knew they were coming. Admiral Chester Nimitz's codebreakers had given the Pacific Fleet the most valuable commodity in warfare: foreknowledge of the enemy's intentions. Machinist Myers stood at his station in the fuel control room, monitoring pressure gauges and flow rates as Yorktown launched her strike aircraft. Dauntless dive bombers and Devastator torpedo bombers roared off the flight deck, their tanks topped off with aviation gasoline that had flowed through the purged distribution lines. Myers had personally supervised the CO2 purge after the fueling evolution was complete, watching the pressure gauges as carbon dioxide displaced the residual fuel vapor from the trunk lines. The system was working exactly as designed. Those fuel lines were now filled with inert gas, incapable of forming an explosive mixture regardless of what damage the ship might suffer in the coming battle. At 1100 hours, radar detected incoming Japanese aircraft, 70 miles out, then 60, then 50. The first wave of Japanese dive bombers arrived shortly before 1118 Aichi D-3 Aval aircraft escorted by Zero fighters. Yorktown's anti-aircraft batteries opened fire, throwing up a wall of flak that detonated in black puffs across the sky. The Zeros came in first, strafing the flight deck to suppress the anti-aircraft guns. Then the Vals rolled into their dives, plummeting nearly vertical toward the carrier below. The first bomb, a 530-pound armor-piercing weapon, struck the flight deck near the center of the ship at 11:27. It punched through the wooden deck planking, penetrated the steel flight deck below, and detonated on contact with the hangar deck. The explosion killed or wounded dozens of men in the immediate vicinity of the blast and started fires among aircraft parked in the hangar. Damage control parties responded immediately, manning hoses and foam equipment to contain the fires. The second bomb hit minutes later, farther forward. This one went down the ship's funnel, the massive exhaust stack that vented smoke from the boilers. The bomb exploded inside the uptakes, rupturing steam lines and blowing out boilers. 5 of Yorktown's 9 boilers were knocked offline immediately. The ship's speed dropped from 30 knots to 24 knots, then to 6 knots, as the engineering crew fought to maintain power with their remaining operational boilers. The third bomb struck aft, starting fires in a rag storage compartment on the 4th deck. This was exactly the kind of hit that had started the chain reaction aboard Lexington. A fire in a space adjacent to fuel storage and distribution systems, with damaged ventilation trunks that could carry smoke and potentially spark into areas where gasoline vapor might be present. Myers watched his instruments, looking for any sign that the fuel systems were compromised. The pressure readings remained steady. The CO2 purge was holding. What Myers couldn't have known, what nobody aboard Yorktown could have fully appreciated in the moment, was that his unauthorized modification had just prevented the same catastrophic fuel vapor explosions that destroyed the Lexington. The third bomb's explosion had damaged ventilation ducts in the area of the aft fuel trunks. Under normal circumstances, with those trunk lines containing residual gasoline vapor after the morning's fueling operations, that damage would have allowed explosive fumes to leak into surrounding compartments. Eventually, inevitably, a spark from electrical equipment or a flash from the fires would have found that vapor. The explosion would have killed dozens of men and started secondary fires that would overwhelm the damage control parties. But the fuel trunks didn't contain gasoline vapor. They contained carbon dioxide, thanks to Myers's purge system. When the ventilation ducts ruptured from the bomb blast, what leaked into the surrounding spaces was inert gas, not explosive fuel. The CO2 actually helped suppress the fires in adjacent compartments by displacing oxygen. What should have been the trigger for a cascading fuel explosion instead became a fire suppression asset. Commander Irving Wiltsey, Yorktown's executive officer, made his damage control rounds within minutes of the bomb hits. When he reached the aft fuel control station and saw that the trunk lines in the damaged areas were still maintaining pressure with no sign of vapor leakage, he understood immediately what had happened. Myers's system had worked. The executive officer's report, filed after the battle, would note specifically that the CO2 purging of the topside gasoline lines had prevented a serious conflagration. But in the moment, Wiltsey simply told Myers to keep the system operating and moved on to the next damage control station. The fires were brought under control within the hour. The engineering crew managed to restart enough boilers to bring Yorktown's speed back up to 20 knots. At 1300 hours, the flight deck had been patched sufficiently to resume operations. Yorktown began recovering aircraft from the morning strike, landing planes aboard a carrier that by all rights should have been dead in the water or sinking. Japanese aviators from the first wave, those who survived the gauntlet of American fighters and anti-aircraft fire, reported that they'd left Yorktown burning and dead in the water, clearly out of action. At 14:30, a second wave of Japanese aircraft appeared. 10 Nakajima B, 5N Kate torpedo bombers, again escorted by Zeros. These pilots had been briefed to attack an undamaged American carrier, but when they broke through the cloud cover and saw Yorktown steaming at 20 knots with aircraft landing on her flight deck, they assumed they'd found a different ship. It couldn't be the same carrier they'd been told was left burning and crippled 90 minutes earlier. The torpedo bombers split into 2 groups. executing a classic anvil attack, with bombers approaching from both the port and starboard sides simultaneously. Captain Buckmaster manoeuvred Yorktown hard to starboard, attempting to present a narrow profile to the incoming torpedoes. The ship's reduced speed, hampered by the boiler damage from the earlier bomb hits, made evasive action difficult. 2 torpedoes struck the port side near frames 80 and 92, tearing massive holes in the hull below the waterline. The torpedo explosions ruptured fuel tanks, flooded machinery spaces, and severed electrical power throughout much of the ship. Yorktown took an immediate list to port, 17 degrees within minutes. The list was severe, enough that Buckmaster worried the ship might capsize. Damage control parties couldn't reach the flooded compartments to assess the damage or begin counter-flooding measures. At 1500 hours, with the ship listing heavily and no power to run pumps or ventilation, Buckmaster gave the order to abandon ship. Myers was among the last men off, helping to secure watertight closures as the crew evacuated. He'd done everything he could to protect his fuel systems, but 2 torpedo hits below the waterline, directly into the tank spaces, were beyond what any safety system could mitigate. As he climbed over the side and down into the rescue boat waiting below, he looked back at the Yorktown, listing but still afloat, fires under control, and thought about the Lexington. Same class of ship, same design, similar battle damage. But Yorktown was still floating. She hadn't been torn apart by internal fuel explosions. The list was from flooding, not from the catastrophic fires that had gutted Lexington's internal compartments. The destroyer USS Hammond came alongside the abandoned carrier that evening, and a salvage party went aboard. With portable pumps and damage control equipment, they managed to reduce Yorktown's list to just 2 degrees. She remained afloat through the night and into the following day, and there was serious discussion about attempting to tow her back to Pearl Harbor for repairs. Then, on June 6th, the Japanese submarine I-168 found the crippled carrier and put 2 more torpedoes into her hull. One of those torpedoes also sank the Hammond, which was alongside providing power to Yorktown. The carrier finally rolled over and sank the following morning, June 7th, 1942, but the lesson had been learned. Admiral Nimitz's official report on the Battle of Midway, filed on June 15th, included a specific section on fuel system safety. The report noted that gasoline fires on carriers represented a serious menace to ship survival, and that Yorktown, though hit by 3 bombs and set afire, had experienced no gasoline fires, possibly because of the effective use of CO2 in the gasoline system. That single sentence, buried in a 30-page after-action report, represented official recognition of Myers's modification. The Bureau of Ships received Nimitz's report on June 20th. By June 25th, there was a directive going out to all aircraft carriers in the Pacific Fleet. Implement CO2 purging systems for aviation fuel distribution lines. The directive didn't mention Myers by name. It didn't acknowledge that the system had been installed without authorization. It simply stated that carbon dioxide should be used to purge gasoline lines and create an inert blanket over gasoline tank compartments, preventing the formation of explosive vapor in fuel distribution systems. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engineering specifications arrived in July. The system that Myers had improvised over 3 days in Pearl Harbor was now formalized into official Navy procedure. Carrier construction yards received modification packages detailing exactly how to install CO2 purging capability into existing ships. New carriers under construction, the Essex-class vessels that would form the backbone of the Pacific Fleet for the rest of the war, incorporated CO2 purging systems into their fuel handling designs from the keel up. The modification wasn't complex. It didn't require exotic materials or sophisticated engineering. It was essentially identical to what Myers had fabricated aboard Yorktown: copper tubing running from CO2 storage bottles to connection points on the main fuel distribution trunks, with simple valves to control the purge flow. The entire system added perhaps 200 pounds of equipment to a ship displacing 30,000 tons. Installation time ran between 40 and 80 hours, depending on the ship's configuration and the availability of the modification crews. But the impact was enormous. Between July 1942 and the end of the war in August 1945, the U.S. Navy commissioned 17 Essex-class fleet carriers, 9 Independence-class light carriers, and dozens of escort carriers for convoy protection and amphibious support. Every single one of those ships went to sea with CO2 purging systems installed in their fuel distribution networks. Not one of them was lost to internal gasoline vapor explosions. That's not to say carriers didn't burn. They did. The war in the Pacific was brutal, and Japanese kamikaze attacks in 1944 and 1945 caused terrible fires aboard multiple carriers. The USS Franklin, hit by bombs while operating off Japan in March 1945, suffered casualties exceeding 800 killed. The USS Bunker Hill, struck by 2 kamikazes in May 1945, lost nearly 400 men. But these casualties came from the direct effects of enemy weapons: bombs detonating in hangar decks, aircraft catching fire, ammunition cooking off in the heat. They didn't come from fuel vapor explosions propagating through the ship's internal fuel distribution system. The Franklin survived her damage and made it back to Pearl Harbor under her own power, despite fires that burned for hours and explosions that devastated her flight deck and hangar spaces. Her war damage report, filed in April 1945, noted specifically that the ship's gasoline system had been secured and purged with inert gas before the attack. When the bombs hit and fires broke out, there was no explosive vapor in the fuel distribution lines to propagate the disaster into spaces that weren't already burning. Post-war analysis by the Navy's Bureau of Ships attempted to quantify the impact of Myers's innovation. The math was straightforward but sobering. A Lexington-class carrier had a crew of approximately 2,800 officers and men, plus an air wing of another 850 personnel. When Lexington went down at Coral Sea, she lost 216 men, about 6% of her total complement. That casualty rate reflected the fact that the ship had time to evacuate most of her crew before the fuel explosions became catastrophic. A carrier suffering internal fuel vapor explosions during combat operations, with battle stations manned and damage control parties fighting fires throughout the ship, wouldn't have time for an orderly evacuation. Based on the explosion patterns observed aboard Lexington, where 3 major fuel vapor detonations occurred over a span of 2.5 hours, an Essex-class carrier, experiencing similar failures during active combat, could reasonably expect casualty rates between 30 and 50% of all personnel aboard. With a complement of 3,300 officers and men, that translated to between 990 and 1,650 casualties from a single ship loss. Over the course of the Pacific War, U.S. carriers engaged in dozens of major battles where they took significant damage: the Battle of the Philippine Sea, the Battle of Leyte Gulf, the Okinawa Campaign, the strikes against the Japanese home islands. In many of these actions, carriers were hit by bombs or torpedoes that damaged fuel systems. The USS Enterprise was hit multiple times. The USS Intrepid absorbed 4 separate kamikaze strikes. The USS Hancock, USS Ticonderoga, USS Randolph, all took damage that, aboard Lexington with her unpurged fuel systems, would likely have resulted in catastrophic fuel vapor explosions. Conservative estimates suggested that the CO2 purging system prevented at least 3 carrier losses that would otherwise have resulted from internal fuel explosions. 3 carriers, at roughly 1,300 casualties per ship based on combat conditions, came to 3,900 lives saved. Rounding to 4,000 was reasonable given the uncertainties in casualty projections. But the impact extended beyond just preventing ship losses. Carriers that survived battle damage and returned to service represented continued combat capability throughout the war. A carrier that might have been destroyed by fuel explosions instead received repairs, returned to the fleet, and conducted additional combat operations. The Enterprise, arguably the most famous carrier of World War II, survived the entire war despite taking heavy damage multiple times. Her survival meant continuous air support for Marine and Army operations across the Pacific, from Guadalcanal to Okinawa. How many ground troops survived because Enterprise's aircraft were available to provide close air support? How many amphibious landings succeeded because Enterprise and her sisters could maintain air superiority over the landing beaches? The second and third order effects of keep carriers operational multiplied through every level of the Pacific campaign. Carriers that didn't explode from internal fires could recover damaged aircraft that would otherwise have ditched at sea. Pilots who might have been lost were instead saved, returned to duty, and flew additional missions. The cumulative effect of these cascading benefits made any precise casualty count impossible, but the direction was clear. Myers' system saved thousands of lives, both directly by preventing ship losses and indirectly by keeping carriers operational throughout the war. Myers himself never received official recognition for the innovation. There was no medal, no commendation, no mention in the official histories of carrier operations in World War II. The Bureau of Ships Directive implementing CO2 purging systems didn't cite his work or acknowledge that the system had been developed by a machinist operating without authorization aboard a carrier preparing for combat. The engineering journals and technical reports published after the war credited the system to collaborative development by Navy Department engineers and Bureau of Ships technical staff. This wasn't conspiracy or deliberate suppression. It was simply how military bureaucracy processed innovations that arose outside official channels. Myers had violated regulations by modifying Yorktown's fuel systems without proper authorization. Acknowledging that violation, even posthumously, and even though the modification had proven life-saving, would have complicated the Navy's institutional position on the importance of following specifications and procedures. Easier to simply incorporate the innovation into official specifications and move forward as if it had been planned that way from the beginning. Myers survived the war. He'd left Yorktown before she sank and was reassigned to the carrier USS Wasp later in 1942. He served aboard Wasp until she was torpedoed and sunk by a Japanese submarine in September of that year, but Myers again survived and was rescued. He finished the war working in the Navy's fuel systems training school, teaching the next generation of machinists how to operate and maintain carrier aviation fuel systems, including the CO2 purging procedures that had become standard throughout the fleet. After the war, Myers returned to civilian life. He worked in commercial shipbuilding for several years, then moved to the petroleum industry, where his expertise in fuel handling systems translated into refinery operations. He retired in the 1960s and died in 1976 at the age of 68. His obituary mentioned his Navy service during World War II, but made no reference to his role in developing the CO2 purging system that had become standard equipment on every aircraft carrier in the world. Because by the 1970s, CO2 purging wasn't just an American innovation anymore, it was international maritime standard practice. The British Royal Navy had adopted similar systems during the war, after American and British naval architects began exchanging technical information in 1940. The Royal Navy's carriers had used a somewhat different fuel storage design, with cylindrical tanks surrounded by seawater, but they'd experienced similar problems with gasoline vapor accumulation in distribution lines. British carriers incorporated CO2 purging into their fuel handling procedures by late 1942. The Japanese never figured it out. Analysis of captured Japanese carriers after the war revealed that their fuel systems lacked any provision for inert gas purging of distribution lines. This contributed to the catastrophic losses at the Battle of Midway, where 3 Japanese carriers, Akagi, Kaga, and Soryu, were destroyed by relatively modest initial damage from American dive bombers. The bombs started fires on the hangar decks, and those fires propagated through the ship's fuel systems, causing secondary explosions that gutted the carriers from within. Japanese damage control doctrine emphasized fighting fires directly with water and foam, but provided no mechanism for eliminating explosive vapor from fuel distribution systems before fires could find them. Post-war carrier design, both American and international, incorporated fuel system inerting as a fundamental requirement. The principle extended beyond CO2 purging of distribution lines. Modern carriers use nitrogen-enriched air to maintain inert atmospheres above the fuel in storage tanks, preventing ignition of vapors in the tank spaces themselves. Fuel lines are automatically purged with inert gas whenever they're not in active use. Ventilation systems that might carry fuel vapors are segregated from electrical equipment that could provide ignition sources. The Forrestal fire in 1967, a catastrophic accident aboard the carrier USS Forrestal that killed 134 sailors and injured hundreds more, demonstrated both the effectiveness of modern fuel-inerting systems and the continuing danger of aviation fuel aboard carriers. The fire started when a Zuni rocket accidentally fired from one aircraft into another, rupturing a fuel tank and starting a massive fire on the flight deck. The fire spread rapidly through parked aircraft, each loaded with fuel and ordnance for strike missions over North Vietnam. But the fire didn't propagate into Forrestal's internal fuel distribution system. Despite temperatures hot enough to melt aircraft and cook off bombs, despite fuel spilling across the flight deck and draining into lower decks through ruptured drains, the carrier's internal fuel systems remained inert and didn't contribute to the disaster. The casualties were terrible, the damage was extensive, but Forrestal didn't suffer the kind of cascading internal fuel explosions that had destroyed Lexington. The ship survived, was repaired, and returned to service. That survival can be traced directly back to the fuel-inerting principles that Myers had improvised aboard Yorktown 25 years earlier. Modern nuclear-powered carriers, the Nimitz class, and the newer Gerald R. Ford-class ships, carry even more aviation fuel than their World War II predecessors. A Nimitz-class carrier stores approximately 3 million gallons of JP5 jet fuel, roughly 10 times the capacity of a World War II Essex-class carrier. That fuel must be stored, distributed, and handled safely despite the enormous quantities involved. The fuel systems aboard these ships incorporate multiple layers of safety features: nitrogen inerting of storage tanks, automatic purging of distribution lines, leak detection systems that can identify vapor escapes before they reach dangerous concentrations, and sophisticated damage control systems designed to isolate and suppress any fires that do occur. All of these systems trace their lineage back to that makeshift modification Myers fabricated in Pearl Harbor. In May 1942, the core principle remains unchanged. Replace oxygen with inert gas in any space where fuel vapor might accumulate, making it physically impossible for an explosion to occur regardless of ignition sources. The implementation has become vastly more sophisticated, with automated controls and electronic monitoring replacing manual valves and pressure gauges. But the fundamental insight, that preventing the formation of explosive mixtures is more reliable than trying to eliminate ignition sources, came from a machinist who understood that his ship was going into battle with a lethal vulnerability and decided to fix it whether or not regulations authorized the modification. There's a memorial plaque at the Naval History and Heritage Command in Washington, D.C., listing innovations developed during World War II that contributed to Allied victory. It's a long list: radar, proximity fuzzes, torpedo improvements, damage control procedures, countless engineering, advances that gave American forces technological advantages over their enemies. CO2, fuel system inerting, appears on that list, credited to the Bureau of Ships, Development Division, 1942. Oscar W. Myers's name doesn't appear anywhere on the plaque. But every sailor who's served aboard an aircraft carrier since 1942 has benefited from his work, whether they know it or not. Every pilot who's landed aboard a carrier and taxied to the refueling station, every aviation machinist who's maintained fuel systems, every damage control party that's fought fires aboard a carrier without having to worry about fuel vapor explosions propagating through distribution lines. They're all protected by a system that began with one machinist, 3 days in port, some copper tubing, and the determination to prevent his ship from dying the way Lexington had died. The mathematics of military logistics are brutally simple. Ships that survive battles can fight again. Sailors who don't die in fuel explosions can serve throughout the war. Carriers that remain operational provide continuous air support for every operation, every landing, every battle. Myers's unauthorized modification didn't just save the sailors aboard Yorktown. It saved the sailors aboard every carrier that came after, every ship that benefited from CO2 purging systems incorporated into their designs, every crew that fought fires without having to worry that the fire would find explosive vapor in the fuel lines and tear the ship apart from within. 4,000 sailors is a conservative estimate. The actual number is probably higher, perhaps much higher when the indirect effects are considered. But even at 4,000, that represents 4,000 fathers who came home, 4,000 sons who survived, 4,000 men who lived to see the end of the war, because a machinist understood that regulations and specifications weren't as important as keeping his shipmates alive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.